In this example, we are dealing with a uniform rod of mass m and length L. And in a previous example, we established that the angular frequency of this rod was square root of 3g over 2L. What that means is that the 3g, if we write it like this, it's square root of g over 2/3 L. That means that the mass, or sorry, the long uniform rod oscillates back and forth the same way that a point mass of length 2/3 L would oscillate. And we've seen the videos for that. Okay, so, but what makes this problem more interesting is that we are going to actually add an effect to it. This is supposed to be like a wall, and maybe it should be further to the left, but I want to connect a spring to it. When I connect a spring, I have ideal spring of, draw a little bit more below, spring constant K. And what you'll observe if you do this experiment is that the pendulum will oscillate, but it'll oscillate at a different rate because of the presence of the spring. And so how do we analyze this? The problem is what would be the period of the spring? Or what would be the period of the pendulum now? Which of course you need the angular frequency. So let's look at this. Let's look at this rod. Look at the forces that are acting on it, and see if we can get something that looks like simple harmonic motion. So two things: the spring is always horizontal. It's just meant to be horizontal in this problem, and a more realistic, a more realistic problem would actually have like two springs. Something like this. We got one spring on one side and a spring on the other. And so it'll kind of oscillate kind of back and forth. Now you might think, well, it's not drawn to scale. Shouldn't it go in a circular path? Yeah, it should, but for small oscillations, and that's exactly what we're concerned with here, for very small oscillations, this circular path is very nearly horizontal. And so that's the approximation that we're going to make. We're going to assume that sine theta and make the small angle approximation. So in looking at these torques, we have mg vertical and the spring force is horizontal actually. And so how are you going to figure out the torques that these two apply? Well, if we're going to talk about this, we have to have a coordinate system. And I'm going to use a coordinate system where the positive angle theta is given counterclockwise to the negative vertical. Okay, that's just the convention that we can use. It doesn't matter. But calculating, so both of these forces, the gravity force and the spring force, those both exert torques around about the rod at its maximum spot. So what is the expression for the torque due to gravity? Well, this should be familiar because it was in the previous sections, but you have a moment arm of L over 2 and a force that points straight down. Right? To calculate the torques, of course, you got to, the easiest way that I remember is to match the force and the R vector at the same spot and do the right-hand rule to calculate the torque. This is minus theta, because you always go from R to F when you're calculating torque. And so you should get that the gravitational torque in this case is minus magnitude of the force times magnitude of the moment arm times sine of theta. So that's the torque due to the gravity force causing it to oscillate. And sure enough, if that was the only torque, then the thing would oscillate as we expected. But there's also the second torque. There's this spring torque, this different one, and it's horizontal. So what are we to make of the angles? First of all, what's the magnitude of the force anyway? You might think, well, spring force equals minus kx, right? That's not going to help us because what's x? I mean, in this case, the spring force that this feels that the rod feels comes from the displacement from the equilibrium. And that's like a delta S actually. That's not a delta X. It's a delta S where you're assuming that the spring was in equilibrium when the rod was hanging straight down. That's the only thing you reasonably presume. Because since the path is more like a circle, then the displacement delta S actually equals L delta theta. And so the expression for the spring force, the magnitude of it is actually K times L theta. That's the magnitude of the force. So, but let's calculate the torque now. Now to calculate the torque, you got a long L, and you have a force like this. Okay, so what is the angle? Draw a little bit better. What's the angle between these two? Well, we know this is theta. But the angle from L2 to F is phi. And so phi is equal to pi over 2 plus theta. So the expression for the torque here then is the spring torque. It is still minus because we're moving clockwise. So it's minus the magnitude of the force, which is KL theta, spring constant times distance, times the entire length, times sine of phi. But interestingly enough, if you take the sine of phi, you remember what's one of these trig identities, that sine of pi over 2 plus theta actually equals cosine theta. And if you don't remember, just think about what happens when theta is 0. Right? When theta is 0, you have sine of pi over 2 is 1, cosine is 1, so it is positive. As you know, as the angle increases, the sine goes up, the cosine goes down. They both decrease. So it's actually cosine of theta. So yeah, this is minus k L squared theta times cosine of theta. So you have two torques here, and I'll kind of leave the space on the bottom here to finish off the calculation. They're in the same direction, so they have the same sign. So we got net torque equals minus mg L over 2 sine theta minus k L squared theta cosine theta. And that equals the moment of inertia of the rod, which is 1/3 ml squared, times the angular acceleration of the rod, which you remember is d squared theta dt squared. So that's the general expression if it was released from a very large angle. Fortunately, the small angle approximation, in the small angle approximation, you have sine theta is approximately theta. Cosine theta, if you've never seen it, you might be pretty surprised. No, it's approximately 1. And why is cosine theta approximately 1? Well, if you look at the graph of cosine theta, right? It starts, like this. So you zoom in on the cosine graph, very close to 0, it looks just like 1. And the further out, it looks like 1 minus theta squared over 2. So in the small angle approximation, this sine theta turns into theta, and the cosine just goes away. It just turns into 1. And so, in fact, factoring out in a lot of algebra, you show that factor out the minus sign, bring that out front. That's mgl. Factor out the theta, bring it on the right. That's plus kl squared theta. And then you got moment of inertia that equals 1/3 ml squared. Of course, that came from the moment of inertia of a rod around its edge. oops, times d squared theta dt squared. And so if you divide by 1/3 ml squared, you see that there's some interesting things that happen. I forgot the 2 here. Yeah. So multiply, so the m's cancel in the first term, the L squareds actually cancel in the second term, and you're left with get d squared theta dt squared equals minus, excuse me, equals minus 3g over 2l, just like the pendulum without the spring, plus 3k over m times theta. So that's a little algebra that we did, and sure enough, we see that the resulting oscillation of this rod, when subject to not only gravity treating it like a physical pendulum, but also the spring adding to the oscillation, is that you get a larger angular frequency. So just for completeness then, I'll show that the angular frequency is then the square root of all that. 3g over 2l minus 3k over m. And then the period then is just 2 pi over that. So that's a little bit harder to calculate. So we'll just leave it at that. The period is 2 pi divided by this answer. But one thing that I want to highlight is that if you square this thing, then the angular frequency squared of the rod with the spring force, it's equal to the square frequency of the pendulum plus 3 times the frequency of the mass spring system, if squared. It has to be squared. And so in this sense, you see that the angular frequencies kind of add together in a sense. The only thing is that because we're dealing with a rod, not a point mass, then that extra factor of 3 from the moment of inertia shows up in the angular frequency of the mass spring part of it. So this is a more advanced question example, but it really highlights how we use Newton's laws, how we use physical laws to show the angular frequency of an oscillating system. And that's something that I want us to carry forward into future classes, future chapters, because there's always going to be a system that oscillates in all of the chapters that you cover in this class. A mass on a spring was just like one of the first ones. So that is it for this example.